Hi everyone, thank you for your interest in our paper. This is Sangwoon Kwak and Weeyoung Kwon from Electronics and Telecommunications Research Institute and Chung-Ang University. Today we are pleased to present our work, MoRel. To begin with, MoRel is designed for 4D novel view synthesis. It reconstructs a dynamic 4D scene from calibrated multi-view videos and synthesizes novel views that can be rendered in real time. In other words, given captured videos from multiple viewpoints, the model can generate visually consistent scenes from unseen viewpoints. This is important because such technology enables immersive applications, including VR and AR, 3D displays, telepresence, and other interactive visual systems. To better explain our method, I will first briefly introduce 3D Gaussian splatting, or 3DGS. 3DGS represents a scene with 3D Gaussians and renders images through splatting. It is optimized with differentiable rendering from SFM-based initialization. Due to its simple design and strong performance, 3DGS has become a standard method in NVS. It achieves both high quality and fast rendering speed. Based on this success, it has naturally been extended to dynamic scenes. As a result, various 4D Gaussian splatting methods have been proposed to model dynamic motion with reasonable quality. This suggests that Gaussian-based representations are also effective for dynamic scene reconstruction. However, most 4DGS benchmarks evaluate only short clips, usually around 150 to 400 frames. This means current evaluation settings are still limited to relatively short temporal ranges. In contrast, real-world videos are often much longer and commonly contain several thousand frames or more. So there is a clear gap between benchmark settings and practical long-range scenarios. To handle such long-range videos, existing methods mainly follow two directions: all-at-once training and chunk-based training. The first approach is all-at-once training, which directly loads a long-range video and optimizes the entire sequence within a single canonical space and a single deformation network in a brute force manner. However, as the video becomes longer, this unified representation easily leads to either memory overflow or limited representational capacity, resulting in underfitting. The second approach is chunk-based training, which divides the video into smaller chunks and trains them separately. This avoids memory overflow and maintains reasonable capacity within each chunk. However, it often produces temporal flickering artifacts at chunk boundaries, which degrades temporal consistency. For long-range evaluation, we newly composed self-cap LR based on the original self-cap dataset. As shown in the table, self-cap LR exhibits larger motion magnitude and a wider camera baseline than existing benchmarks. This makes it a more challenging benchmark for long-range 4D reconstruction. This figure illustrates the characteristics of our newly composed self-cap LR more clearly. Compared with previous benchmarks, it contains both larger motion and wider camera spacing. Therefore, it provides a more realistic and challenging setting for long-range evaluation. To address these limitations, we propose MoRel. Its core idea is anchor relay-based bidirectional blending, which relays keyframe anchors over time to achieve both bounded memory and smooth temporal transition. The results on the right support this idea more clearly. Compared with all-at-once training, our method maintains bounded memory usage while preserving higher representation fidelity over long-range sequences. Compared with chunk-based training, it shows a more stable TOF curve and a more continuous temporal profile, indicating better temporal consistency. In summary, MoRel achieves both memory efficiency and temporal coherence for long-range 4D reconstruction. Our second key idea is progressive windowed training. A naive chunk-wise training of bidirectional deformation causes inter-chunk interference, especially backward contamination. As a result, updating the current chunk can corrupt motion that was already optimized in previous chunks. To address this problem, we divide the training into two stages: progressive windowed deformation and interframe blending. First, progressive windowed deformation optimizes only a local window, which prevents interference across chunks. Then interframe blending smoothly connects adjacent windows, preserving temporal continuity without interchunk corruption. At this point, a key question is how to connect neighboring keyframe anchors more naturally. To address this, we introduce our third key idea, learned opacity control for blending. Inspired by exponential decay-based opacity modeling, we assign learnable offsets and decay speeds to adjacent keyframe anchors. Then the left anchor is deformed forward and the right anchor is deformed backward toward the intermediate time step. Finally, the two deformed anchors are blended with learned opacity weights to produce a smooth temporal transition. The next slide shows why this learned opacity control is necessary. A simple linear blending often produces blur and ghosting in the transition region. In contrast, our learning-based blending generates sharper and more temporally coherent results. Our fourth key idea is feature variance-guided hierarchical densification, or FHD. We use anchor feature variance to measure local frequency complexity and assign hierarchical levels accordingly. First, in variance-based leveling, anchors are grouped into different levels according to their feature variance. This allows us to distinguish low-frequency regions from high-frequency regions. Then, in level-wise densification, densification is controlled differently for each level. As a result, low-frequency structures are stabilized first, while high-frequency details are progressively refined later. This hierarchical strategy enables more efficient capacity allocation under bounded memory growth, so FHD improves detail recovery without causing unnecessary densification. Based on these key ideas, this slide presents the overall architecture of MoRel. Our framework is built on anchor relay-based bidirectional blending, or ARBB, for long-range 4D motion modeling. It consists of two phases, the anchor relay phase and the bidirectional blending phase. Anchor relay phase. First, in the GCA stage, we learn a global canonical anchor by skimming the entire sequence, which provides global consistency. Then, in the KFA stage, we learn high-quality representations for key moments. These keyframe anchors also serve as local canonical anchors for each chunk. Bidirectional blending phase. In the PWD stage, we progressively train the bidirectional deformation fields associated with each keyframe anchor. This allows each local window to model motion stably while avoiding inter-chunk interference. FB stage, we learn interframe representations by blending neighboring key anchors through learned opacity control. This enables smooth transition between adjacent anchors and improves temporal continuity. To make this pipeline more concrete, let me now walk through the algorithm and figure stage by stage. We start from the GCA stage. Here we train a global canonical anchor from the initial point cloud and the entire sequence. At this stage, the goal is to build a globally consistent base representation before the anchor-wise loading pipeline begins. Next, in the KFA stage, we sequentially load each keyframe anchor initialized from the global anchor. After training the current keyframe anchor with FHD, we immediately unload it. In this way, we keep only the currently required anchor in memory. In the PWD stage, we load the current keyframe anchor together with its bidirectional deformation field. Then we train only the local bidirectional deformation window for the current anchor. Once the optimization is finished, we unload both the anchor and its deformation module before moving to the next one. Finally, in the IFB stage, we load only two neighboring keyframe anchors and their deformation fields. We then learn the blending parameters between them through learned opacity control. After the blending parameters are saved, the loaded modules are again unloaded, which keeps the memory usage bounded throughout the full long-range sequence. We evaluate MoRel on SelfCap-LR, our long-range multi-view benchmark curated from SelfCap. It contains 5 scenes with up to 24 views and around 3,400 to 3,600 frames per scene. For evaluation, we use PSNR, SSIM, LPIPS, and TOF, and compare our method with both all-at-once and chunk-based baselines. First, compared with all-at-once methods, MoRel achieves the best overall quantitative performance. This is because all-at-once training tends to suffer from either memory explosion or limited representation capacity on long-range videos. In contrast, our method maintains bounded memory while preserving high representation fidelity. Next, compared with chunk-based methods, MoRel also shows superior performance. Conventional chunk-based training often suffers from temporal inconsistency and flickering at chunk boundaries. By contrast, our bidirectional blending produces smoother transitions and better temporal consistency. Beyond PSNR, SSIM, and LPIPS, we further analyze metrics that are particularly important for long-range videos. As shown here, MoRel keeps memory usage bounded through on-demand loading, unlike all-at-once methods. At the same time, it achieves the best TOF, indicating stronger temporal consistency than chunk-based methods. We also compare qualitative results on frames sampled at long intervals in self-cap LR. Compared with previous methods, MoRel produces sharper details and more stable appearances over time. These results show that our method preserves both visual fidelity and temporal consistency in long-range scenes. Beyond the quantitative results, we also provide demo video comparisons. First, this slide compares MoRel with all-at-once training on long-range sequences. As the video becomes longer, all-at-once training struggles to maintain sufficient representation capacity over the entire sequence. In contrast, our method preserves sharper details and more stable motion while keeping memory usage bounded. To evaluate the effectiveness of each component in MoRel, we conduct an ablation study. We begin with a simple baseline that uses only a single global canonical anchor with uni-deformation. While this preserves overall consistency, it is not sufficient for modeling detailed local motion. As a result, it yields the lowest reconstruction quality. Next, we introduce keyframe anchors as local canonical anchors. This improves local motion fidelity and also greatly reduces both training and rendering memory through localized anchor modeling. We then add progressive window deformation with linear blending. This further improves reconstruction quality by reducing inter-chunk interference with only a modest increase in training memory. However, simple linear blending is still limited in handling irregular motion. To address this, we replace it with inter-frame blending, which performs adaptive bidirectional blending between neighboring anchors. By replacing linear blending with IFB, we obtain clear gains in PSNR and LPIPS. This shows that adaptive bidirectional blending is more effective for irregular motion transitions. Finally, we apply FHD, or Feature Variance Guided Hierarchical Densification. With FHD, we achieve the best PSNR while also reducing rendering memory. This demonstrates a better balance between reconstruction quality and memory efficiency. This ablation compares the number of hierarchy levels used in FHD. When the level is 1, it is equivalent to not using FHD since densification is not hierarchically divided. With 2 levels, anchors are split into 2 groups and controlled separately, and with 3 levels, they are further divided for finer densification management. As the number of levels increases, reconstruction quality improves while storage decreases, indicating more efficient capacity allocation. As shown in the table below, FHD maintains similar performance under different variance threshold settings for level assignment. Although the threshold values change, both reconstruction quality and storage remain largely stable. This indicates that FHD is not highly sensitive to the exact threshold values. Similarly, FHD also maintains stable performance under different level-wise importance weights for densification control. Even when the weight configuration changes, the overall quality remains stable while storage stays reduced. This shows that FHD is also robust to the specific densification weight settings. The top row visualizations show how different hierarchy levels contribute to reconstruction. Lower levels mainly recover the coarse global structure, while higher levels progressively add finer details. For example, regions such as the hand, bicycle structure, and clothing folds become clearer at higher levels. The bottom row FFT results further support this observation from a frequency perspective. Lower levels emphasize low-frequency components which correspond to coarse structure. In contrast, higher levels contain stronger high-frequency responses, indicating that they capture finer details. This analysis further shows that FHD level-wise rendering captures both spatial and motion frequency. Lower levels mainly represent the overall background structure, while higher levels recover complex motion and fine details around the person and object boundaries. By applying FHD, we reduce the number of anchors from 266,610 to 222,764, which corresponds to a 16.4% reduction. Despite using fewer anchors, the rendering quality remains nearly unchanged. This demonstrates that FHD improves representational efficiency by suppressing redundant densification. This analysis examines the effect of GOP size. The results show that reconstruction performance remains largely stable across different GOP and hexplane configurations. This suggests that GOP should be selected based on system requirements such as storage budget and access granularity, rather than as a performance tuning hyperparameter. This slide analyzes the overall training time of MoRel. Although MoRel requires more iterations than 4DGS, the overall training time remains reasonable. This is because each stage maintains relatively high throughput with smaller hexplane configurations and shorter observation windows. We also evaluate generalization on the monocular dynamic scene benchmark, die-check iPhone. MoRel achieves the best average PSNR while maintaining competitive SSIM and LPIPS. This shows that the proposed design generalizes effectively even to challenging monocular dynamic scene reconstruction. In addition, we evaluate generalization on hyper-NIRF, di-NIRF, and panoptic sports. MoRel achieves competitive or the best performance on these benchmarks. This shows that our design maintains high reconstruction fidelity across diverse datasets even without dataset-specific tuning. In conclusion, we presented MoRel, an on-demand loading-based long-range 4DGS framework for flicker-free and memory-bounded dynamic scene reconstruction. ARBB coordinates keyframe anchors and bidirectional deformation with learnable temporal opacity to achieve coherent motion transition. In addition, FHD improves high-frequency detail recovery while suppressing redundant anchor densification. As demonstrated on SelfCap-LR, MoRel achieves sharper reconstruction, smoother temporal transition, and lower memory consumption. Finally, let me conclude with the limitations and future directions of our work. Our current method is still challenging to extend to spatially larger scenes and can be sensitive to time-varying spatial changes. In addition, transitions from the global canonical anchor may still introduce some inconsistency. For future work, we plan to explore spatial grid integration, frequency-aware representation, and a unified framework for large-scale spatiotemporal modeling.